Hello everyone, I'm Ximeng Liu. It is my great honor to present our paper today titled Geminet, Learning the Duality-based Topology-Agnostic Update Operator for Lightweight Traffic Engineering in Changing Topology. This work is co-authored by Zhuoran Liu, Yingming Mao, Yatao Li, my PhD advisor Shizhen Zhao, and Xinbing Wang. Let's first briefly review traffic engineering, or TE for short. Given a network, it distributes the traffic between each source destination pair across multi-candidate paths so that the load on different links is balanced and the hotspot link can be avoided. As shown in the figure on the left, there are several candidate paths from A to F. What the TE solver needs to decide is the fraction of traffic carried by each path, where all these fractions sum up to 1. The inputs include the topology, the demand metric, and the candidate path set for each node pair. The destination variable is split ratio on each path. The objective is usually to minimize the max link utilization across the whole network, which we commonly refer to as MLU. A lower MLU means the network is less likely to become congested, and it also leaves more headroom for traffic bursts. TE is widely used in real-world systems. In wide area network, such as Google's B4 and Microsoft's Xi'an, operators need to continuously redistributed traffic as demand changes. In data centers, architectures such as Google's Jupyter, which use optical circuit switches, can dynamically reconfigure the topology at runtime. In these settings, TE must react after each topology change. So what makes a good TE algorithm? We believe it should satisfy at least 3 requirements at the same time. First, high quality. The split ratio it produces should reduce MLU as much as possible. Second, scalability. The number of nodes and links in modern WAN and data centers is growing rapidly, so the algorithm must be able to keep up. Third, topology adaptiveness. Once the topology changes, for example, when a link fails, a new link is added, or an OCS is reconfigured, the algorithm should remain usable without retraining or redeployment. As for network performance, we all want it to be better, so there's not much to explain here. Let's first look at scalability. As the network becomes larger, the dimensionality grows on both the input and output sides. The solver needs to process more topology and traffic variables, and it needs to decide more split ratios. Therefore, we need a TE algorithm that can handle this growth. As for the topology adaptiveness, in WAN and data centers, topology changes are not real events. They are the norm. Link may fail and nodes may go offline. Capacities may be upgraded and new links may be added. In data centers, OCS can even directly reveal the topology at runtime. All these changes can alter the graph structure, the link capacities, and the candidate path set. Therefore, after such events, a TE algorithm must produce a valid split ratio solution. It cannot simply say, please wait a few hours while I retrain a new model. With these 3 requirements in mind, let's revisit existing approaches. The classical approach is linear programming. We formulate the entire TE problem as an LP and solve it using solvers such as Groby. The advantage is solution quality. LP-based method can produce optimal solutions, but the cost is speed. Solving time becomes the bottleneck. Once the network becomes large, the runtime can quickly become unacceptable. To improve speed, learning-based TE methods have been proposed, such as DOT. The key idea is to train a neural network to learn the mapping from demand to split ratios. During inference, it only needs 1 forward pass, so it can be extremely fast. However, early learning-based models have a critical limitation that they can just be applied by one topology. Once the topology changes, the model no longer works and has to be retrained. To address this issue, the most representative recent work is HARP. Its approach is to stack topology-aware neural models inside the model. It uses a GNN to graph neural network to encode the topology, and a transformer to encode paths, and a recurrent adjustment unit model to adjust the each path's split ratio. This thus provides the topology adaptiveness. When the topology changes, the model can still run directly. But the cost is also clear. The model's computation grows when the topology size, path length, and the number of paths. In other words, HARP solves the adaptiveness problem, but gives up a part of scalability. Although its inference time is still fast, but computational overhead during both training and inference becomes higher as the network grows. We then analyzed and decoupled the scalability issue into two main sources. First, stacked topology encoding models. To feed the graph and the path into the model, methods like HARP have to stack multiple graph neural network or transformer layers. As the depths increase, both computation and memory costs grow accordingly. Second, the path-level decision space. These methods learn a state variable for each candidate path. However, the number of candidate paths grow with the number of nodes. As the network gets larger, the number of paths quickly become very large. Therefore, we propose Geminet with two target design to address these two bottlenecks we just discussed. We take topology encoding out of the learnable part of the neural network and move the update operation from the path level to the edge level. So the design one is a topology-agnostic update operator. This replaces the stack of neural models that have to read the topology and decouples the neural network from the topology. As a result, the same operator can be applied across different topology without retraining. And the design two is a Duality-based transformation that moves the decision space from path to edge. Okay, now I will introduce design one, topology-agnostic update operator. Overall, a learning-based TE method wants to use neural network to approximate the TE solver. The solver takes the demand metric, the topology, the candidate path, and the link capacity as input, and outputs the optimal split ratio. There are two ways to achieve this solver. The first is the one-shot solver. The network takes in the entire graph, all paths, and all capacities, and outputs the final split ratio. Since the network has to understand the topology, it needs to stack the topology encoders. And the second is an update solver. Instead of predicting the final solution directly, the network only approximates one update step. In each round, the network observes a few features of the current state and output a correction similar to the one gradient step in SGD. After multiple iterations, it gradually converges to a good solution, which is a very common idea in a traditional optimization algorithm. Specifically, instead of feeding the raw graph into the neural network, we replace it with 4 scalar features derived from the MLU objective. At each iteration t, for each path p, we compute a 4-dimensional state vector. These features capture both local and global signals, and including the bottleneck link on the graph and the demand of the source dissipation destination pair and the global MLU. The important point is that once the split ratio is given, computing these features can also be viewed as a kind of topology encoding. However, it is not a learned topology encoding. Instead, it is a fixed and deterministic computation derived from the first-order effect of the split ratio on MLU. So the topology and the path still matter, but their information is projected into scalar features rather than encoded by trainable graph neural network or transmission model. This gives us two benefits. First, the neural network is always four-dimensional, independent of the network size or path length. Second, the topology encoding has no learnable parameters, so the same computation naturally applies to new topologies. So far, I have introduced design 1. However, design 1 alone is not enough. Although we no longer need a topology encoder, we still need to maintain a state for every candidate path and update this path level states. As shown in this table, Geminet has only 72 edges, but 1,848 paths, about 25 times the number of edges. For KDL, the gap becomes even more extreme. The number of paths is 1,268 times the number of edges. So with the design 1 alone, the computation required to maintain all these path level states can still be too expensive on large networks. The network-based idea is promising, but we need to move it out of the path space. So how do we move it out of the path space? We take the dual of the capacity constraint, partial dual of the capacity constraint, and obtain a dual variable, lambda, for each edge. Initially, intuitively, lambda E can be understood as the congestion price of that edge. The total number of dual variables is only the number of edges. As we saw earlier, the number of edges is 1 to 3 orders of magnitude smaller than the number of paths. More importantly, linear programming durability tells us that the information content in the dual variables lambda is sufficient to recover the optimal path split ratios. Therefore, instead of updating in the primary big O of path space, we update in the much smaller big O of edge space. In particular, a key observation from our derivation is that once we obtain the optimal solution of the dual problem, the solution to the original primal problem can be recovered very easily. More importantly, the recovery can be done independently for each source destination pair, as shown by the formula in the upper left, without losing optimal. This formula actually has a simple closed form solution. We simply choose the cheapest path, where the cost of a path is defined as the sum of the dual variables lambda over all edges on the path. To make this recover can be trained during training, we replace the argmin with softmin. This closed form solution then serves as a bridge between the dual variables and the primal variables. Following a similar gradient-based analysis as in the primal space, we can derive the scalar features needed for updating the dual variables. And these features are listed at the bottom of the slide. The overall of Geminet is follows. Step 1, we initialize the edge-level dual variables lambda using a heuristic method, since the lambda can be interpreted as a potential congestion price. Step, we then enter the iterative process. In each iteration, we update lambda using the topology-agnostic edge-level update operator and recover the split ratio from lambda using softmin. The process repeats until the preset time budget is reached. Because Geminet keeps iterating between the dual variables and the primary variables. It is like a pair of twins. That is where the name Geminet comes from. Okay, now let's look at the evaluation results. The first set of evaluation focused on the topology changes. We compare Geminet directly with HARP on dynamically changing topology. The conclusion is straightforward. Geminet achieves comparable T equality to HARP, but with much lower overhead. Specifically, Geminet uses only 4% of the GPU memory and achieves up to 3.6 times faster time to reach the targeted performance. The result showing the GPU memory footprint of different methods across topologies of different scope. The takeaway is simple. Across every network we tested, Geminet has the lowest GPU memory footprint. As the network scale increases, the advantage becomes even more pronounced. The third set of results showing two aspects of being lightweight. On the left, we compare the number of model parameters. On the largest topology, KDL, Geminet uses only 0.04% to 7% of the parameters of other methods. On the right, we show the time to reach the target performance on KDL. Geminet is 18 times faster than HARP. Due to the time constraint, I only cover part of the evaluation here. More results are available in the paper. Finally, let me conclude. Geminet makes topology adaptive learning-based TE lightweight. It achieves this through two key ideas. First, a topology-agnostic update operator, and second, edge-level dual variables, which moves the iterative state from the path state to the edge space. Together, these two designs make Geminet both efficient and adaptive to a new topology. This is all for my presentation. If you have any question about the paper, please feel free to contact me. Also, my spoken English is not very good, so I apologize in advance if I cannot fully understand your question during the Q&A. We can discuss offline. Thank you very much.